Welcome, everyone. Oh, I'll try and block this on with my head. Right, so today it is differentiation and integration day for the first year. So we're going to be talking about what is in differentiation and integration in the first year. And I'm going to be very briefly talking about all apart from areas under curves. The most thing I'm going to work on today is areas under curves. So I've got a few classics to go through with you because I think that's the bit that is neglected a little bit in terms of timing. Ages is spent on how to integrate and equation of a tangent, equation of a normal, all that sort of stuff. And then an areas under curves just kind of gets done too quickly, I think, in a lot of cases. So that's what I'm going to spend most of the time on. Okay, that all right with everybody? Let me show you my iPad and we can get started. If it will let me show you my iPad. Sure. Right. So this is the overview of the whole pure thing that we started with at the beginning of the week. And we discussed all of it, and exponentials turned out to be something that people haven't done much of. Now, exponentials takes a lot of practice because it's algebraically fiddly. It's not really that you have to conceptually understand anything or memorize really complicated things or loads of formulas, only 3 rules. But because algebraically it's slightly clunky for your brain, you're not used to dealing with things like 2 to the x. You're much, much more used to dealing with x squared. So your brain is much, much more inclined to think about roots than it is to think about logs. And because your brain likes roots, I bet you didn't when you first started. I bet you think back to school when you first learned about square roots and surds and dealing with them, your brain won't have really liked them at all. It would have felt really uncomfortable. And that's where your brain is with this. But because there's something up in the air and something up in the air, what your brain is going to do, perfectly natural, is go, oh, it's okay. I know about this. It's roots. So if I give you an equation that says, for example, 7 to the x add 1, you'll find loads and loads of people doing the 7th root, thinking that the 7th root is the opposite of 7 to the power of, which it isn't. So that's what we talked about before. We haven't done linearizing data with logs, which is that last bit. I'm going to ask you during this lesson at some point what you want to do tomorrow, because we could do linearizing data with logs tomorrow, or we could do vectors. We could do whatever you like. So plan for today is that I'm going to remind you of how important integration is. And the fact that we looked, in fact, that looks like a little face, doesn't it? Important. Mr. Important. This is so important for next year. It's the foundation of so many marks in the A level. So please go back to that one if you didn't watch it yesterday, or even if you did watch it, please go back to it and practice and practice and practice those trig things. Today is about differentiation and integration. Okay. So integration, what do we actually need to know? Not a lot. It's the opposite of differentiation. You only need to integrate number, oh my goodness. Rules of action hours, people. You didn't tell me the rules. We can't start work until we have a timer on and a clear focus. Okay, the timer is ready. The clear focus for the next 45 minutes is that we're going to talk through everything you need to know about integration and differentiation in the AS Maths A level. And we're going to do some practice of finding difficult areas under curves. Okay, that is our clear focus. And our timer is going on now. And then we have to have a 10 to 15 minute break at the end. So what do we need to know about integration? Integration and differentiation are the opposite of each other. Integration works like this. You have a number, and then you have an x, and you have a power. Now, what I teach and what I recommend that you do, just because it keeps control of all of the fractions and minus signs and stuff, when you're integrating, I'm just going to use an arrow for now to mean integrate. And I do this myself. This isn't like some patronizing, like, oh, why don't you do this? You poor people who can't integrate. I literally, this is what I do when I'm integrating. And it's because for a million billion times, my FFS journal, my silly things, is when I try to increase a power and then divide a fraction by a fraction all in one go in my head, because I think I can do it. and it turns out I can't. So this method forces me to just slow down, and then I don't make as many mistakes. I still make mistakes, but I don't make as many mistakes. So there's the number. Put empty brackets there and just leave them sitting there. Then write down the x. Now have a look at that n. The n is going to go up by 1. So always just think up 1, or maybe even better than up would be add. So often mistakes here will be when the power is -2, and people will increase the power from -2 to -3 because 3 seems bigger. So it's add 1 onto the power, and then when you've added it on, put it upside down in there. Just stick it in upside down. So for example, if I had something like -2x to the -3/2, then I would write down -2 empty bracket x. Now I'm going to add 1 to that. And now as a final step, I'm going to turn that upside down and write it in the bracket. And then you can see that what I get here is 4x to the -1/2. So it's a way of controlling the letters and the numbers and that kind of thing. That's how to integrate. When do we integrate? 2 reasons to integrate. Reason number 1 is that I tell you what dy by dx is, and then I say, what is y? Or other notation, I tell you what f prime of x is, and then I say, what is f of x? Now I have seen ones as well that were nice and sneaky. Last year, one of last year's papers, or the year before, it gave you the second derivative. Not the first derivative, the second derivative, and then said, what's the original function? So you had to integrate twice. Now, when you integrate, I'm sure you know, you get a plus c on the end, because we don't know whether or not there could have been a number on the end there. It might not have been, but we have to put that plus c on the end, and it's often forgotten, as I'm sure anybody that's learned this topic knows. My sister always says plus c. My sister doesn't know anything about A-level maths, but because she lived with me for a while and both my children did A-level maths, and one of my children is now a maths teacher, plus c is just all the time when I was marking. Oh my God, students, plus c, plus c. So my sister, that's the only thing she knows about maths is that plus c is really, really important. So you should try to learn that as well, plus c. So when you integrate, you get this plus c. This one, you'd integrate twice, you'd get a plus c, and then you'd also get a plus d on the next time. So you need to sub in numbers to find that information. So I tell you that y, you say to me y equals da 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 da, you've worked it out, but it's got plus c on, and I say, all right, well, when x is 2, y is 7, and then you can work out the plus c. So that's the first reason for integrating, to get the function back. I guess the second reason for integrating is just because someone told you to integrate. So if someone tells you to integrate, then you integrate. The second reason is the areas under curve. So it's finding a section of area there. And that's the bit where it gets a little bit tricky. Okay. That's it for integration. There is nothing else for integration in the whole of the first year. It's just increase the power by 1 and then divide by the new power. The reason you do that is to maybe to get the original function from the derivative, or the original function from the second derivative, or maybe you're finding an area under curve. No, nothing else. That's the whole thing. The limits of integration that you use, say this is a 4, and actually I'm just going to call this the top limit, and I'm going to call that the bottom limit. When you're finding areas, we start at the bottom limit and finish at the top limit. Okay, is the stream buffering? I can't really tell, it just says a warning on it, so I'm not sure if it's buffering. So I will carry on regardless. Okay, great. Yeah, so we've got the bottom limit and the top limit. I meant to write bottom there. There's your function that you're going to integrate. And then what you do is you put the top limit in first. And then you do a nice big minus sign to show the examiner that you know that there's a minus sign there and that you are doing the limits and everything so that we can award this mark. And then you do the bottom limit. So you stick in x is the top limit minus stick in x is the bottom limit. And that's it. That's the whole of integration. Let's look at differentiation. Differentiation, how do we do it? Well, you've got number x power, and when you differentiate, that n goes down, so you get alpha times n, and then after it's come down, so we're going in the opposite direction in terms of our thinking than integration, then it goes down by 1. So this is now going to be n minus 1. So the complete opposite of the thinking process for integration, we pull it down, then we take 1 off. Whereas with the integration, we add 1 on and then we divide. So that's why it goes wrong, because the order in which you have to think switches. So that's why those brackets on the integration can be really, really helpful. Right, why would we differentiate? Well, maybe because we're told to. Maybe the question is, what is the derivative of a particular thing? Or maybe they phrase it differently. Maybe they say y equals blah, blah, blah. What's dy by dx? Or the second derivative, the derivative of the derivative. They might say, what's the second derivative? Or they could use the other notation. F of x is this. What is the derivative? Or what is the second derivative? So that's one situation in which we'd use differentiation. We're literally just told to differentiate. Okay, another situation in which we might differentiate is to find the equation of the tangent or the equation of the normal. These are just straight lines. So we know how to do straight lines, hopefully. I always use this form, mx minus a is y minus b, but you can flip that round and have y minus y1 is mx minus x1 if you prefer. Please don't use y equals mx plus c. Y equals mx plus c, and then shoving things into it and rearranging to find c is the most common way of losing marks in the actual exam. So of course everyone knows how to do it, but it causes mistakes because it's more work than using this structure or the other way around. So y equals mx plus c, I'm just telling you from my experience of examining, students who use y equals mx plus c as the structure of a line tend to make more mistakes and get fewer accuracy marks at the end of the question than students who use x minus a is y minus b or y minus y1 is mx minus x1. So why do we need differentiation? For the m, for the gradient of the tangent. So the gradient of the tangent is dy by dx, and you've got a dy by dx button on your calculator and you'll see it looks like this. And what you can tell your calculator to do is find the derivative at a point. So that means you can check your differentiation. Second years can do this as well. Differentiate it, stick a point into your derivative, and then use your calculator, and then you stick the x in there, and your calculator will tell you the gradient of the tangent, which is pretty good. If it's the normal, and so many, I mean, if you look on proper mark schemes, you will see that in the notes, any question on the tangent or the normal, we tell the examiner what to do for a candidate that does the opposite. Because so many people, if we set a tangent question, do the normal, or if we set a normal question, do the tangent. And it's so common that the mark scheme actually tells the examiner in advance what to do. We write that before we even look at any scripts because we know that loads and loads of students will do it. So don't make that you. It's tangent or normal. Make sure you know the difference. The normal, you still need to find dy by dx because that's the gradient of the tangent. But then because it's perpendicular, negative reciprocal. Flip it upside down, change the sign. This is all the stuff you learned in geometry at the beginning of the AS. Flip it upside down, change the sign, you've got the gradient of the normal. And then the gradient of the normal would go in that position there. So that's another reason why you might differentiate, to find the equation, tangent, and the normal. You might be looking, there's loads more reasons to differentiate than integrate. You might be finding stationary points. So stationary points, maximums and minimums. Well, I should say max, min, and inflection. There's a type of point called an inflection point that looks like this. And it might be a stationary point or it might not. So some inflection points are stationary, but some inflection points are not stationary. All maximums are stationary, all minimums are stationary, some inflection points are stationary. The definition of stationary mathematically is that the first derivative is 0. So you are finding the first derivative, putting it equal to 0, solving that equation and finding where it's got a stationary point. To find out whether it's a maximum or a minimum, you need the second derivative. And then you sub in the point that you already found, and you find out whether or not it's maximum or minimum. So for a maximum, second derivative is negative. For a minimum, second derivative is positive. That's all you need to know about differentiation. The optimizing problems tend to cause problems for students, but all an optimizing problem is this. But at the beginning, they get you to do annoying simultaneous equations, okay? But basically, optimization is find the derivative, put it equal to 0, solve it, and then decide whether or not it's a maximum or a minimum. So the only addition is that we need to do plus simultaneous equations. And that's the bit that students hate, which is fair enough because they tend to be really, really fiddly simultaneous equations. Sad face. Or maybe happy face if you like manipulating algebra. First principles proof. That is where you use the actual definition of a derivative. The limit as h tends to 0 of f of x plus h minus f of x all over h. Now, if you don't recognize that formula, that means that you've got a gap in your knowledge. If you do recognize it, then you know what I'm talking about. It's always the same formula. We're sticking it in, and it's a way of proving that the derivative is pull the number down and take one off. Like we know the derivative of x cubed is 3x squared. Why is it? And using first principles, it actually proves that the derivative or the gradient of the tangent of the function x cubed at a particular point is 3x squared. So that needs learning. Right, playlist wise for this week, let's go back to the integration. So for the playlist, for 24 hours after the lesson, the playlist videos are totally free in the content guide. You have a link to the content guide in your Exambulance, and you can click on the content guide and then you can go to these numbers, 38 and 39, and they will be able to be watched for the next 24 hours. Okay. So it's 38 and 39 is the playlist, plus these ones here, 34, 35, 36, 37. So 6 in total. They're about 10 minutes each. So it's an hour to make the notes, not loads. Tristan will talk at the end about what you want me to do tomorrow. And we'll just have a vote of whoever's here at the end of this session. We'll have a vote about what you would like for tomorrow. Okay, right. Areas. Here is my tip for you to get us started. It's that we're going to have a particular color. So I'm going to use red. And the rule is that this particular color, you can have whatever color you like, but you have to start on the x-axis and go up to the curve, or start on the x-axis and go down to the curve. That is the rule, okay? So start on the x-axis. Here's the x-axis. And just draw lines to the curve. Like that. Start on the x-axis. Do dots on the x-axis, whichever dots you think might be helpful, and then you go up to the curve or down to the curve. And then we're just going to use this to help us to work out what to do. Now, let's see why this is important. Let's have a look at something a little bit more complicated, and then we'll come back to these, okay? First of all, I just want to show you what the red line does. Okay, now it's looking more tricky, but the same rule applies. We have to put our dots on the x-axis, and then we have to draw lines to the curve. Okay, same here. Draw dots on the x-axis, and then lines to the curve. Like that. There's one more to show you. Dots on the x-axis, and then lines to the curve. Now look at this one. Lines to the curve, not the line, the curve. The curve here is x cubed. Yeah, areas below we'll come back to. I just want to show you, first of all, what these red lines do, how they control it. So go from the x-axis up to the curve or down to the curve, and this is the curve. Okay, same thing here, x-axis, and then go to the curve. Don't worry about, for now, what is happening or what you're doing. Just always start off in integration and areas under curves. Just start it off with this rule that whatever your favorite color is, have this rule that we start on the x-axis and we go up to the curve or down to the curve. Now, can you see that with that last one, I went to the line, not the curve. This is the curve. I want to go to the curve. So I should be going like this. There's the curve. There's the curve. Okay. There's the curve. There's the curve. And that's the end. Okay. These are the ones we're going to look at today. So that's step number one. Step number two is that we decide what we're going to do. In these two cases, it's pretty straightforward. We're just going to integrate, but usually there's this extra job. So that's obviously the origin, and that's the bottom limit. That's the first x. And then this one here, that's going to be the top limit. That's where we stop, but I've got to work it out. And this is really common. Quite often you have to work out either a x-intercept or a turning point, like a max or a min, or another type of point, like maybe I tell you the y coordinate and you have to find the x coordinate. So quite often there's these little jobs to do. Another little job might be simultaneous equations. Or maybe factorizing, all sorts of stuff that we might have to do in order to get that bottom limit and that top limit. But the bottom limit and the top limit are always x values. The third derivative, what does the third derivative tell you? It tells you, well, I mean, it tells you all sorts of stuff, but the big thing it tells you is whether or not what you think might be an inflection point is or is not an inflection point, okay? So inflection points are all about the second derivative and nothing to do with the first derivative. An inflection point might be stationary, it might not be stationary. But in order to find out whether or not something that we think might be an inflection point, second derivative is 0, is or is not an inflection point, we use the third derivative as a test. Just like the second derivative tests whether or not you have a max or a min, the third derivative tests whether or not your inflection point is or is not an inflection point, if you see what I mean. Okay, bottom limit, top limit. So in this case, pretty easy. Bottom limit is 0. What's the top limit? Well, let's solve x. 2 minus x is 0. So either x is 0 or x is 2. So the top limit is 2. And this is what we need to work out. Now, from this point, it's integrating. So we'll come back and do that later. For now, I want to talk about setting up the actual integrals when you're looking at that area. So next one, here is the bottom limit. And well, here is the top limit, really. That's what we might be tempted to do. But someone mentioned earlier, the areas below the x-axis. Now, what this is doing, the whole of integration, what it's doing is making little rectangles and adding them up. So when I go across doing the integral, even though it doesn't look like it's doing this, this is what it's doing. And every little x all the way across, it's doing this width times this height to get that area. And it's doing this width times this height to get this area. So how does it work out the height? It literally sticks the x into the function to find out how high it is. Now, algebra doesn't know that if that comes out negative, it means it's a negative y coordinate, which means it's below the axis. The algebra is just going, right, I wonder how high it is at x is 4, and then shoving x is 4 in and then going, oh, it's -7 high. So it just carries on like that, but it uses -7 as the height. So all of these little boxes here, when you're integrating, all of these little boxes come out as negative areas. So if I tell the algebra to go all the way from that bottom limit, all the way to the top limit, and tell me the whole overall area, it's going to go wrong, because it's going to work out this area. Let's say that area is like 3. And then it works out this area down here, which is like, say that area is 6. Then algebraically, it will be -6. So I'd have 3 there and -6 there. So it would say altogether -3. And that's not what we asked. We asked for an area. So we have to be really careful to think about the difference between an area and an integral. So this is what we do. We introduce a new top limit here. And that equals the bottom limit of the next one. And we do 2 separate integrals. First of all, well, what are these? Let's work it out. Here's the job. We always have a job at the beginning of an integration problem. So the job is, when is it 0? So we have either got x is 2 or x is -1 or x is -4. So this one must be the -4, this one must be the -1, this one must be the 2, which means our limit is -4 to -1. Okay. Correct, Tristan. If you chuck it all in your calculator, it will give you the integral, not the area. So what we're doing here is finding the integral. This is the integral. And in this particular case, from -4 to -1, this integral equals that area. And this integral equals that area. Now, the integral I'm about to write down doesn't equal the area, this one. It's going from -1 to 2. Okay, and this integral does not equal that area. Oops. Integral doesn't equal area. So I can work it out. I can work out what it is, the integral from -1 to 2, blah, 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 but it's not the area. The way that you make it the area, and this seems really counterintuitive, but the way you make it the area is you times it by -1. So when I get this area coming at this integral, sorry, I'm going to do this integral. And this is really, really, in the second year, this gets so tricky fiddly, because the things that pop out have all sorts of letters in them. And you can't just look at it and think, oh, -26, areas aren't negative, 26, which is what first years do. And then in the second year, it comes out P ln a third plus K. And you're like, okay, so the answer is P ln a third plus K. No, not if the graph was below the axis. If you want the area, you have to multiply the integral by -1 to get the area. If the area is above the axis, then the integral equals the area. But this bit here, is this a highlighter? There you go, sort of covered it up, didn't it? Times -1 is the area. Integral times -1 is area. 4 sections below. Yeah, they are really, the graphical calculators are amazing. Although, having said that, I've got one, and this is the one that I usually use. That's partly because I spelt gin and tonic on my really expensive one, and now like some of the buttons are a bit sticky, like 0 and divide. So it's a bit annoying. I have to like, so that's partly why I use that one. But you're right, if I was doing A-level, then I would invest 50 quid and get the Casio CG FX CG50. FX CG50. I definitely, yeah, exactly. CG, yeah, I would. Right, next. So what do we need to do here? We've done the first rule, which is to go from the x-axis to the curve. Okay, now we have a look at it, and what we're going to be using is all of these shapes. So rectangle, A, B, the area is A times B. Square, A, the area is A squared. A triangle, A, B, the area is a half AB. This triangle, there's the base, there's the height, the area is a half AB. A trapezium, lots of people don't know the trapezium one. It's A and B added up, they're the parallel bits, and then you times it by half of the distance between them. And that's the area. So these are the shapes that we're going to be using with integrals. It's going to be either shape plus integral, integral plus shape, same, or maybe integral minus shape, or maybe shape minus integral. And these are the ones that students find difficult. But if you start off with the red dots and the red lines, it's going to be a lot easier. Now, I hope that you can see with this one that what we've got here is a rectangle. But we're going to take away that area there, which is an integral. Anything with the red lines is an integral. That's what an integral does. It gives you the area from the x-axis up or from the x-axis down. So this is going to be an integral. And this is going to be an integral. And this bit in here is going to be an integral. The red lines show you the integral. Same thing as always now. Okay, so we're going to be doing some jobs, extra jobs at the beginning of integration, always extra jobs. So the extra jobs in this case will be like, I don't know what this is, but I do know that y is 4 at that point. So if I go into the equation and put 4 is the square root of what, then I get the x. So the jobs that you have to do, they're always something slightly different every time, but you'll see it comes back to always the same things. Finding an x-intercept, finding a turning point, finding the x-coordinate of a certain point. And then that gives you the information that you need to form your shape and your integral. So in this case, this would be 16 here. And we would be doing 4 times 16 to get the rectangle, and then we'd be taking away the bottom limit is 0, the top limit is 16, and the equation of the curve is x to the half. That's what we do. And it's okay, the integral equals the area because it's above the axis. It's only difficult if it's below the axis. Because that area is above the axis, then this area and this integral are the same. Integral equals area. Okay, next one. Right, well, this just looks really confusing. But what if I draw this little shape? Oh, see? Area of a sector is a half r squared theta, where theta is in radians. Look at this shape. Can you see that it's the exact same? That was 9 there. That y-intercept is 9. So if I want to go across here and find out what that is down there, then I'd say, well, the y-intercept is 9. So x cubed is 8. So x is 2. And another job, always with integration, these little jobs, I have to find this bottom limit. So the bottom limit, well, that's where x cubed plus 1 is touching the x-axis. So that would be x cubed plus 1 is 0. So x cubed is minus 1. So x must be minus 1. So all of these little jobs that we do at the beginning. Now we're going to do the exact same thing. I'm going to do the whole rectangle. It goes from minus 1 to 2, so that's 3 across there, and it goes up to 9. And then I'm going to subtract the red area. See that red area? And I would never have seen that unless I'd put all my little red lines on. It would have been really difficult to spot that that's what I needed to do. It's okay. The integral and the area are the same because it's above the x-axis. So what I'm going to be doing is 3 times 9 minus the integral from minus 1 to 2 of x cubed plus 1 dx. That's what we do. Okay. These two. Now, can you see that first one now? Have a look at the first one. And while I write on these, you have a look at that first one and see if you can work out what to do. And the second one, it's going to be an integral and a shape, but what integral and what shape, and do the extra jobs at the beginning. I'll give you a few minutes just while I write these things down. Okay, so first one is, well, that red bit I do actually want, so I'm going to find that integral, and then look, it is a triangle. So the first bit that I want is going to be the integral from 0 to, oh, another job. Always, always another job. So here's the job. I don't know what that is. So this is a simultaneous equations, isn't it? Two graphs crossing. So I need to know, where does x cubed cross 2 minus x? Where does x cubed plus x minus 2 equals 0? Now then, what are we going to do with this? This is what happens with integration. It's not actually the integration that's hard. It's working out, it's doing the extra jobs and working out what shape has been added or subtracted or combined with an integral. The integrals are the red bits. The red bits are formed by going from the x-axis up or the x-axis down. If you go x-axis up, then the integral and the area are the same. If you go x-axis down, then the integral times minus 1 is the area. So we have this problem, this extra problem, and until I work out what to do with it, I don't know that top limit there. But I do know that when I've found it, I will be working out how far across that is, and then I'll be able to do it. So all these extra jobs, algebraic division. So yes, but the trouble with algebraic division is that we know what to divide by, right? We're trying to solve a cubic. The only way that we can solve a cubic is to factorize it. So I need to factorize it. That's just a fact, okay? It's a cubic. I want to solve a cubic. I can only solve a cubic by factorizing. There's no cubic form. Actually, there is. There's a cubic formula, a quartic formula, and a quintic formula, like the quadratic formula, but we're not using that. It's disgusting. It's so messy. So it's a cubic. I need to solve it. I need to factorize it. How can I factorize it? Algebraic division. Problem: I don't know a factor. Now, this is in the new A-level spec. I do have a calculator, but I'm not going to get marks for using a calculator unless I cheat and pretend I worked it out. So I need to at least, you're completely right. Stick it in the calculator, find the roots, and then work backwards. But this is what they're expecting you to do in the new spec. And it is called spotting a root. Now, can you think, if I put a particular x in, is there any way that I can make that naught? Clue. It's going to be 1 minus 1, 2 minus 2, 3 minus 3. Exactly. Ibrahim's right. Try 1, try minus 1, try 2, try minus 2. I think they could probably go as far as 3 and minus 3, but that would be it. So in this case, exactly, f of 1. Right, f of 1, if f of x is this guy here, then f of 1 is obviously 1 plus 1. Minus 1 plus 1 minus 2, which is 0. So that means, factor theorem, that x minus 1 is a root. And now I can do my lovely, lovely algebraic division, which I love. This is not algebraic division. It's synthetic division. I don't like algebraic division. You don't need it in the new spec. It was needed in the old spec. It's not needed in the new spec. We can do it like this. 1x cubed, no x squareds, 1x and a minus 2, dividing it by x minus 1. 1 goes there, 1 times 1 is 1, add them up, 1 times 1 is 1, add them up, 1 times minus 2 add 2 is not that. There's my quotient. I know that f of x is equal to x minus 1, x squared plus x minus 2. How cool is that? That is how easy synthetic division is. It's so good. So why was I doing all that? All of that was so that I can find out where those two cross. This has got a negative discriminant. So there's no solutions. There's only one crossing point. That's how I can tell there's only one crossing point. The synthetic division I won't go through, but what I will do to be nice to you is I will add the synthetic division to the freebies for the next 24 hours, okay? So you'll be able to find it. It's called factor theorem and algebraic division, okay? I don't remember what number lesson it is. Yeah, polynomial division is, oh my God, we had to do it before because students had to divide by quadratics, but now you don't have to, so now we can do that method. It's called synthetic division. I don't think it's called the grid method. I think that's something else. Anyway, the point is that this guy here, all of this stuff, this was a really big extra job. And all of that work that I just did, spotting that I could factorize a cubic, then realizing what the factor of the cubic was, and then using some sort of division that you're happy with to get the other factor so that I can work out what that crossing point is. And now I know that's a 1, so that goes there. Still not done. Because look at the triangle. I don't know how high the triangle is and how far across the triangle is. So I've got all this work to do too, and I haven't even started integrating yet. Okay, what's happening here? Well, the line 2 minus x is crossing the x-axis. So if 2 minus x is 0, x must be 2. That was pretty easy. So this is going from 1 to 2, so that's 2 across there. What about the height? Well, to get the height, I could put the 1, yeah, I need to find the y, and I could put it into either of them because that's where they cross. So 2 minus 1 or 1 cubed, both of them give me the answer 1, which means the height here is 1, which means this is 1. And now I'm ready to integrate. Note, you do not need to know algebraic polynomial division for Edexcel 100%. No, you do not. You are only going to be asked to divide by linear factors. You need to know, right, let me be very clear. You need to know how to divide a cubic or a quadratic or a quartic by a linear function, ax plus b. You need to know how to do that. You do, but that means that doesn't mean that you need to know how to do algebraic division. Yeah, I think the teachers are all teaching it because they taught it last year and the year before and the year before for the last forever, because the actual specification changes the words in the spec. It has gone from saying being able to divide to being able to divide by a linear function only. And that's just a tiny tweak. And what that means is that you no longer have to teach algebraic division and that you can teach this method called synthetic division instead. But I think a lot of teachers just didn't realize that tiny, I mean, this is a huge document, right? I've read it and read it and read it and read it and read it. And also because I do examining, so I have to know the spec really, really well to know what types of things we need to put in the mark scheme. Okay, so this method is on the AS, it's in the content guide, and it is called factor theorem and algebraic division, and I will add that to the next 24 hours of freedom for you, okay? Right, last one, is this the last one? Yes, last one. So I can see, because I did the red area, I can see that I am going to be finding this whole thing, which, oh, extra job, don't know what that is, always an extra job. But once I've worked out what that is, my red area goes from 0 to whatever that is. And the curve equation that I'm going to is x plus 1, x 5 minus x. Now, that's obviously not the area I was asked for, but look, here is a right angle triangle. So if I take that off, then I'll get the area I want. Is it wrong to find the factor x minus a using first guess, then long division? Well, when you do long division or synthetic division, you do need to be dividing by something that you know. Otherwise it is, oh my goodness, messy mess. So yeah, you would find the factor. Yeah, you find the factor using guess. So then I knew it was x minus 1 is a factor. And then you can use whatever division method you like to get this other thing here. I guess with this particular example, because I can see that there's only one crossing point, that means I already know that this only has one root, which means I know that when I find that root, I know that it's that one because there is only one. So maybe in this particular case, I actually wouldn't have needed to do the division and get the quadratic to know that there weren't any other roots. You're probably right. Okay, we have 3.5 minutes, so I'm going to finish this one off and talk about the jobs that we need to do for this one. So how are we going to find P? Well, this is the only job type that I haven't shown you yet, that we haven't talked about. Let's go back to when we were discussing it. X-intercept by factorizing, making it naught, rearranging, turning point. Okay, turning point. We've done the simultaneous equations, we've had to factorize, blah, blah, but quite often it's a turning point. There it is. So what we would have to do is we would have to expand it out. 5x minus x squared plus 5 minus x, so 4x. That's what y is. Then we'd have to differentiate it. Then make that naught and then solve it for x. Does anyone know a quicker way? There's a quicker way that I could have found out what this guy was without having to do all of that stuff. It's really nice. It's to do with the symmetry of the quadratic. The turning point of a quadratic is always in the exact middle of the roots. It doesn't skew over to one side. It's always in the middle of the roots. And I can see that the roots are -1 and 5. That didn't require any work. I could just look at it. Yeah, minus b over 2a, that's, yeah, I prefer whenever possible to not have a formula. So like distance between 2 points, use Pythagoras. It's not a formula, it's a way of thinking, because you've got 2 points, imagine a right angle triangle. Oh yeah, obvious. So if you use minus b over 2a, you'd still have to actually expand all that out to get the full thing. And then you'd have to identify the a and identify the b and do minus b over 2a. It's a little bit clunky, yeah, but you don't need anything that can be done realistically in your head. We don't need the method for. And we would expect a good mathematician to just know that, oh, wait a minute. Did I get that one wrong? What happens when you expand that out? 5x minus x squared, add 5 minus x is 4, is that. Differentiate it, you get 4 minus 2x. 5 and minus 1, 4 minus 2x, 2, 2. Oh yeah, no, I'm being stupid. Right, so what's the average of -1 and 5? The average of -1 and 5 is 2. I didn't need to do any expanding, any differentiating, any formulas, anything. That is just 2. And in the mark scheme, that would be a B1 mark because it doesn't require any work. If students go off and do a whole bunch of work, then whatever, that's fine. When I see the 2, I'll give you the mark. But we would know that a good mathematician would just look at that 1, look at that 5, go, right, the roots of -1 and 5, they add up to 4, divided by 2 is 2. So that's what goes there. And now I can see that the bottom of the triangle is 2. And I can put 2 into the quadratic to get the height of the triangle. And then I can use the triangle area. So, good timing. So let's do I'm going to cancel this. We have to stop. We have to stop for between 10 and 15. I don't know why I put my glasses off. Now I can't see anything you're writing. Probably because I'm just stopping now. I've done my action hour. Stop. Break. Okay, let's go back to the beginning and see what we talked about. Trig, really important, must practice, can't just memorize. Exponentials, less important, but must practice and fiddly algebraically. Differentiation and integration. We've gone over a summary of what integration is and why you would integrate. And we've gone over a summary of what differentiation is and why you would need to differentiate, the different types of problems, and the fact that you need to know the proof by first principles. And then we've looked at areas under curves. We've looked at the ones above and the ones below. And I've told you about the dots along the x-axis and going up or going down to the curve. And they're going to help you when you get complicated ones like this. But all the complicated ones, if you've done your red lines, it's going to be more obvious to you what you need to do. It's going to be one of these shapes, add or subtract an integral, or an integral, add and subtract a shape. You always have to do these extra jobs. They're quite big in the integration. They are finding out where things cross, finding out the intercepts, finding out the turning points, all sorts of stuff. So all of the algebra comes in order to even get going with the integral. And that, my lovelies, is it for today. I'm going to eat some chocolate buttons. I'm going to have a 10-minute break and then teach the second years all of integration. Don't forget that your exambulance is waiting for you and that you can use the content guide button and go work on some stuff. Oh yeah, I was going to ask you that. So do you still want to do vectors tomorrow? That's what we decided at the beginning of the week. So if we're still up for vectors tomorrow, we'll do vectors tomorrow. We're trying to finish the spec, don't forget. Okay. Okay, vectors tomorrow it is then. See you tomorrow.